All right, today we're going to take one of the biggest ideas in calculus, the derivative, and give it a massive upgrade. We're going to move way beyond just finding the slope at a single point, and instead, we're going to build this incredible new function that tells us the slope, the rate of change, everywhere on a curve.
So how can one graph possibly tell the story of another one's steepness? That's the big question we're tackling today. We're going to see exactly how to create this new graph, the derivative graph, that just perfectly describes all the rises, the falls, the peaks, the valleys of our original function. It's a really beautiful relationship when you see it.
So here's our game plan. First, we'll make that leap from a single point to a whole function. Then, and this is the fun part, we'll visualize how these two graphs talk to each other. We'll also cover the different ways people write this stuff down, look at some cases where the whole thing breaks down, and finally, we'll go one level deeper, literally.
Okay, first up, from a point to a function. So how do we make this huge leap? Well, it actually starts with something you already know, but with this really simple, kind of brilliant twist.
You probably recognize this formula, right? This is the definition of the derivative at one single fixed point A, and it's awesome for finding the slope of the tangent line at one specific spot on a curve. But that's its limit. It's just one spot. And here it is. This is the breakthrough moment. What if we just stop thinking about A as a fixed point? What if we let it be a variable? We do this by simply swapping out that constant A for the variable x. And that one little change, it changes everything. It lets us ask about the slope not just at one point, but at any point we want.
And just like that, we get the derivative function f prime of x. Now, for any input x you plug into this new function, the output it gives you is the slope of the original function f of x at that exact same x value. We've basically built a slope-finding machine that works for the entire curve. It's incredibly powerful.
All right, now for my favorite part, actually seeing this in action. The theory is cool, but watching the relationship between a function and its derivative just unfold visually, that's where it all clicks into place.
So let's take a look at a classic example from the textbook. F of x equals x cubed minus x. It's a nice curvy function that's just perfect for showing us everything we need to see.
So if you try to picture this graph, it's got that classic S shape of a cubic function. It starts low, rises up to a peak, then dips down into a valley, and then shoots back up again. It's a fun little roller coaster.
Okay, so if we do the math and apply that limit definition to our function, what we get is its derivative. F prime of x equals 3x squared minus 1. And this new function, this holds all the secrets to the shape of our original graph.
So what does the graph of this new function look like? Well, it's just a simple U-shaped parabola. But the important thing to notice is where it lives. Sometimes its value is positive, right? Meaning it's above the x-axis. And sometimes its value is negative, dipping below the x-axis. And, most importantly, it crosses the x-axis in two specific places.
Okay, this slide right here, this is the aha moment. Let's walk through this carefully. When our original function, f of x, is going up, when it's increasing, what's its slope? It's positive, right? And would you look at that? In those exact same sections, the value of f prime of x is positive. Its graph is above the x-axis. Now what about when f of x is going down, when it's decreasing? The slope is negative. And you guessed it, the f prime graph is below the axis. Its value is negative. And here's the absolute coolest part. At the very top of that hill and the very bottom of that valley, the tangent line is perfectly flat. The slope is 0. And where's the derivative graph at those exact points? It's crossing the x-axis. The value of f prime is 0. The connection is perfect. It's amazing.
So we've been using this f prime notation this whole time, but it's not the only game in town. There are actually a few different ways to write the derivative, and each one kind of tells a slightly different story. So Lagrange gave us the f prime notation we've been using. Newton liked to use y prime, but this one from Leibniz, dy over dx, this one is super insightful. It really screams a small change in y for a small change in x. But you should know, they all mean the exact same thing, the derivative. And this leads us right into the other big interpretation of the derivative. It's not just about the geometry of a slope. It is the instantaneous rate of change. Think about it, the velocity of a rocket, the rate of a chemical reaction, how fast a company's profits are growing. Whenever you want to know how fast something is changing at a single precise moment, the derivative is the tool you reach for.
Okay, So this slope-finding machine we've built, does it work for every single function, everywhere? Well, not quite. There are a few specific situations where a function isn't what we call differentiable.
And the definition is really straightforward. We say a function is differentiable at a certain point if its derivative actually exists at that point. If that limit gives you a real number. If it doesn't, well, then the function is not differentiable right there.
And the classic poster child for this problem is the absolute value function. F of x equals the absolute value of x. It makes that perfect, sharp V shape. Everywhere else on the graph is totally fine, but right at that pointy bottom, at x equals 0, we've got a problem.
And this is a really important distinction to make. At x equals 0, is the function continuous? Yeah, absolutely. You can draw the whole thing without lifting your pen. But is it differentiable? No. And why not? Because at that sharp corner, you can't draw one single unique tangent line. Coming in from the left, the slope is clearly -1, but coming in from the right, the slope is +1. Since they don't agree, the derivative just doesn't exist at that point.
So let's just wrap this part up. There are basically 3 ways a function can fail to be differentiable. Number 1, it has a sharp corner or a kink, like we just saw. Number 2, it has a discontinuity, a break or a jump in the graph. And number 3, it has a spot where the tangent line goes perfectly vertical, because the slope of a vertical line is infinite, which isn't a real number. Okay, so think about this for a second. The derivative, f prime of x, is a function, right? So there's nothing stopping us from taking its derivative, is there? And that, my friends, opens up the entire world of higher-order derivatives.
This is what we call the second derivative, and we write it as f double prime of x. So if the first derivative tells us the rate of change of the original function, its slope, then the second derivative tells us the rate of change of the slope. It's measuring how the steepness itself is changing. Is it getting steeper faster or leveling off?
And this isn't just some abstract math concept. It has a perfect real-world home in physics. If you start with a function for an object's position, its first derivative is its velocity, how fast it's moving. The derivative of velocity, which is the second derivative of position, is its acceleration. And you can keep going. The derivative of acceleration is the third derivative of position. And that has a name too. It's called jerk.
So acceleration is the rate of change of velocity. But what do we call the rate of change of acceleration? We just said it. Jerk. You feel acceleration when you press the gas pedal in a car. But that sudden jolt when the acceleration itself changes, like when a bus driver slams on the gas or hits the brakes, that's the jerk. It's a perfect example of how these different layers of derivatives describe our world in more and more detail. It just makes you wonder, what would the fourth derivative represent? That's the beauty of this. It just keeps going. Thanks for joining me on this one.